Okay, so let me share the, the screen. All right, so I already put the code on the in our repository. GitHub organization is a private code, so you can later check it, right? So today I want to talk about this 2048, right? So it's a pretty old game, right? So it's like it was very popular in, I don't know, 10 years ago. Yeah, do you know this game?
5 years ago. 5 years.
5 years ago.
Yeah, that's when I played.
And then one like on Saturday, I was playing a Chinese mobile game, right? So which is so there's a mini game inside this Chinese mobile game. I mean the big game is about is about how do you say it's a jianghu. It's about a society where people kill each other using sword, and knife, and basically it's a society that everybody knows martial art, and then they fight, right? They fight against each other, and this is like a Chinese society, right? So basically like it is today, right? So, but this is like the overall scene of this game. But inside this game, there is a mini game. It's kind of like this. It's 2048, right? So it's very like 2048. But there is some difference about the 21. Why? What is the purpose of this mini game? Right? So as you can see, so this is on the right hand side, you can see this mini game is basically like a 2048. But what is the purpose of this minigame? So the purpose of the minigame is to get this weapon. You have to forge. You play as a blacksmith, right? So like a blacksmith. You have to forge this weapon, given certain steps, right? So basically here it says that okay, so you have to after 60 steps, you have to reach the score of 1,000 in order to get this weapon. Right? Otherwise, you cannot get this weapon. And then here are some magical items that you can use to ease the procedure, right? So basically, this is if you compare the original 2048 versus this one, and so you can immediately see the difference, right? So the original 2048 do not have a step limit. Right, so you can play it like a very casually, right? You don't have to worry about okay, so whether this step is the best optimal step because eventually it doesn't count, right? So you just play forever. And but here the most important difference, I think, is now you have to really consider every step whether this step is the best step that you can have. Right, so you must reach certain score under certain steps, right? And if not, you fail, right? And so, and then there are some other things like you can use 4 magical items, which was not in the original game. So the first magical item, I call it a hammer. So if you translate the Chinese, it's called like a heaven hammer is like in Diablo. Ade, can you mute yourself?
Sorry.
Yeah. Okay. So so the hammer's purpose is to you can knock down a square. So you make the square disappear, right? And then there is a second item is called it's basically double the square, double the value of the square. So if the square is 2, then you click on that square, so you get 4. Right? So if it is 4, then you get 8, right? But then the square must be less than 32, otherwise it cannot double the things. And then the third magical item is to add 4 additional steps because right now you have the left you have 60 steps as the upper bound. If you use this item, then you get 64. And then the final one is the most powerful one. It's basically replace all empty squares in the board by 8, which you can imagine you get a very easy let's say bootstrap, right? So from the for your score. Okay, and the third rule is using magic item does not count the step, does not count that step, right? So you can, so yeah, so that's And then if you look at the this the level design that this mini game has, right? So for the level 2 weapon, in order to get a level 2 weapon, you have to reach 200 scores in 30 steps. For level 3 weapon, you get 40 steps. You must reach 400 scores within 40 steps. And then level 4 and level 5 is 60 steps to reach 1,000 score. So the score, right? Now we have to concern about the score. How is the score calculated? It's actually pretty simple. The score is added, right? When a merge happens, right? Every time when a merge happens, you get a score, right? And the merge value is basically the score, right? So let's say if a 2-2, right? Two of the twos merge together, then you get a value, you get a score of 4, right? If 2 fours merge together, then you get a values of 8, right? So this is how the score is computed, right? So that's basically introduce the overall background of this game, the purpose and the motivation of this game, how this game is played. And what is my motivation of doing this presentation and also writing a program, waste my weekend on this thing? It's because after some trials, I found it's basically impossible to reach the score without using any item, right? So I want to prove it. I just want to show that this game is designed on purpose to let players to use item, right? It's not even a valid 2048 game, right? So what I did is I built a game sandbox in Python and replicate the game's rules, score rules, code-like behaviors, and then provide an action interface so that we can explore this sandbox using different strategies. Right? Basically, this is something like every time you want to use AI to solve a game, so basically you need a environment, you need a sandbox of the game, whether you're playing Super Mario or playing StarCraft or playing this 2048, you need some game environment or sandbox. Right now, I don't have, and I just want to implement by myself. Consider this as a practice, right? Or as an exercise, right? And after finish the first step, I can do the second step, exploring the winning strategy using this sandbox. So when I first think about I feel like both of them are not so difficult because you only have this very limited number of actions, like a swipe left, swipe up, right, and down, right? So you only have 4 actions. It seems that there is nothing too much to explore. But eventually, what I spend most time on is actually building the game itself, right? So building the game sandbox itself, right? So, which I found also very interesting, right? So to build so the first step, as I said, is to replicate the game system, right? So you have 4 basic actions: up, right, up, down, left, right, right? And then you have to also to understand, okay, so you have this merge behavior. Can you accurately replicate the merge behavior in your program, right? So basically the merge behavior is defined as when you swipe in a direction, all squares are squeezed into that direction, right? So that means, first of all, the same value of squares in a row will be merged, right? But this merge only happens 1 time, right? So let's say if you have 4, 4, 4, 4, right, in a row. So whether it is vertical or column, I just say if you have 4 fours in a row, then you swipe, then it gives you 8, 8, not 16, right? So this is a very subtle details, but in order to accurately replicate the game, you have to really pay attention to those corner cases, right? And empty squares, if there are empty squares, they are squeezed away, right, in the middle of your swiping procedure, right? Of course, there is also a possibility that the swipe cannot happen, right? So the swipe is invalid swipe because there is no way to swipe it anymore, right? And after the swipe, there is a random 2 pop up in the reverse direction, right? So this is also important. So basically, after you swipe to the left, and then the rightmost column will show up a random 2 in some place, right? In one of those 4 places, right? So this brings the randomness to the game, which also makes the game more, let's say, less deterministic, but more probabilistic, right? And then the second step, so this is like the basic gaming system. And then after the finish the basic gaming system, we have to implement the four items, this 4 additional actions, which is a hammer, double value at 4 steps, and replace to 8. Right? So this 4 things. Okay, so let's first focus on the basic implementation, right? So I mean, so this is a thing that, I didn't refer to any like online code. I just come up with the solution by yourself, but you can also think of this, like how would you implement such thing, right? To basically have a great, to mimic the 200, this 2048 by, implementing those behaviors, right? How is it possible to implement such thing, right? And so eventually what I implement is the following. So I have a board which contains a list of squares, right? And this grid size, people can customize it, and the board has some status, right? Has some state, right? These are the internal state, which is the score and the current step, right? And then the square is interesting, right? The square is actually each square has its left, right, up, down neighbors, right, which points to another square, right? And then these values, once the board is initialized, right, these values becomes fixed, so they become constant. So they're not changing over the whole session. So when you play this, it doesn't matter, right, whether it's a left neighbor, right neighbor, up or down neighbor, they are already fixed once the game is started. Right. Actually, once the size of the board is determined, right, the neighbor information is always a constant, right? Well, for example, for this square, for this yellow square, the left neighbor is always this, and right neighbor is always this, and down neighbor is always this, and the up neighbor is nothing, right? There is no up neighbor, right? So once the grid size is fixed, so this neighbor information is kind of fixed. So what actually changes over time is the value. It's actually not, even though we are considering as a swipe, it looks like you are changing the position, but actually I found out that this is actually a better way to implement that, basically by keeping the neighbor information, by keeping the position information, and only change the value, right? Only change the value. So the value, this is persist over the whole session. So that means when you play this game, this value will change over time, right? So the square will initially be O0, and then afterward it will double the size, double, and this guys. There are also kind of temporary state, which after each move you have to clarify, you have to clear them, right? So something like it's merged, it's updated, it's new, and also the score, you have to clear them, because after each move you have to aggregate all the scores from each square, and then put that into the board score, and then this score get reset to 0, right? So then the breakdown of the whole swipe move, a swipe move on the board means that for each square in the board, you move the square to its neighbors, and the move is actually about an exchange the current value with its neighbor's value. Right. So this is actually the breakdown of a swipe move, right? So and I found that this is actually the very efficient implementation because you are not exchanging the neighbor structure, which doesn't make sense to change the moving the square, like changing, reshifting the list, this kind of thing. You just change the value. You are not changing the list structure, right? And all the pointer things, right? So this is a very efficient implementation, right? And I thought this should do the work, right? So basically, this is my first implementation. So you can basically notice that, okay, so for each, so this is on the board level, right? So for the board level, so I basically have to for loop the squares. Before I for loop the squares, I have to reset the state of all the squares. I have to +1 on the step, and after. And then for each squares, I call this, I move the squares to its neighbor, right? Basically, this direction, let's say, if the overall action is to swipe left, then I basically enumerate over all the squares in the board, and I call each squares to move left, right, to left, and then do the calculation, do the values, right? And then after everything is done, I check whether there is an update overall, and if there is an update, I pop up and random 2 on the right, on the counter direction, right? So that's how it works, right? And of course, it's a move direction has a return value. It's either true or false. It means that whether this action is a valid action or not valid action, right? But what I actually found out, and this actually takes me some time to realize this bug, is actually the orders matter. All right. So you cannot just simply for loop these squares. Well, at least not in this implementation, right? And this actually makes the whole implementation a slightly more complicated, right? Which is actually, I call it a combat system, but probably in the gamer, they have a more professional name. It's basically answers the question that what damage should I calculate first, right? So to give you an idea, like I realize that when you swipe up, swipe down, left and right, the order, so how do you calculate which, like basically this is a calculation, right? So this inside the for loop is your calculation. But then the order of the calculation actually matters, right? And then if you swipe up, you have to calculate from the up to down. If you swipe down, then you have to calculate from down to the up, from bottom to the up. If you swipe left, then you have to calculate from left to right, and swipe right, you have to calculate in this direction, right? So this is actually very, very interesting, which I didn't realize. Okay, so I have to implement something like this in the beginning, right? And then realize that okay, so this is interesting, and this reminds me that if this is if this such simple game requires a mini combat system to take care of the order of damage, right? Then what about StarCraft, which you have like tons of units? Like how do you even manage like what order are you going to like do that are you going to calculate first, right? So this is a very interesting question which I didn't realize in the beginning, right? Okay, so the final interface of the board after this question is solved is actually pretty easy, right? So you can initialize a board which gives you a 4x4 squares, and then you can move up. You can show the board, you can plot the board, and then you can move up. So the example is this is the board, and then you can move up, and then you can see okay, so the 2 comes into the up, right? Squeeze into that direction, and then there is a random 2 pop up in the reverse direction, right? So these are the public measures. You can move left, right, up, down, and show for the board. Pretty simple. That's it.
So to solve the order issue, did you change to a matrix?
No, I hard code the match. I hard code the order, right? So basically, there are only 4 possibilities, right? And then in this case, I just hard code. I just hard coded. Okay, so I generate a sequence which basically looks like this: index, integer of a list of integers, which basically hard code these orders. Right. Okay, so now the first part is finished. We finally have a sandbox which people can play, right, manually. And then the second part is how do we want to let's say explore the best strategy without using item. Right? So this is the first step. This is actually the thing that I want to prove. And I want to prove that this is impossible without using magical items. And then so probably when you play this 2848, you realize there's a kind of like a strategy, right? That said that you always keep the largest number to the corner, right? So this will gives you some advantages so that it will become easier and you can easily get a score at the end, high score at the end. But as I said, right? So first of all, I don't care. I don't really care like what they said. And then secondly, this is a different game, right? So now we have to care about the steps, the number of steps. And then given the limited number of steps, like how do we reach the high score? So what I did is I implement the exhaustive look ahead strategy, right, to find the best strategy. Right? So how does it work? Right. So notice that I have only 4 actions in this game, right? Move up, down, left, and right. Then the reward of action, of taking an action at time j, right, at any time, is basically the delta of the score of the board. So basically, before and after I take this before and after I take this action, what is the change on the board, on the score, right? So this is a delta score plus the reward in the future, right? So that means I have to take like imaginary action in the future, and then I trace it back, and then I calculate, okay, so at this point, if I just make some imaginary move in the future, so what kind of reward do I get, right? Then the best strategy is simply by taking the arch max, right, on this 4, right? So eventually you basically have to calculate the reward on left at time j, reward on right on the time j, reward on up on time j, and reward on b on down on time j. So and then this part is basically the look ahead strategy at time j by making some suitable. So to further explore, to further explain this, basically at time j, right, at the current time, if I take left, then the look ahead strategy basically like explore all the operation, all the possible actions on given certain depths, right? So that means, you know, I have to take the step, and then I look at, okay, so if for the next step, if I take left, and then for the next step, I take left again. So what is the reward there? And then if I for the next step, I take right, what is the reward? So you can imagine that if a look ahead equals 2, then you basically have to explore 4 times 4 times 4, right? 64 strategies, 64 possibilities, right? But don't forget there is a random 2 dropping on the counterpart, right? So if you also take into the consideration of random 2 dropping, basically you have to, you know, you have to make sure that you take the best, you know, your strategy won't be ruined by this random 2 pop-up, right? So then the total number of possibilities that you are going to explore is 16, the cubic of 16, right?
Do you consider always the worst possibility when having?
I consider the mean possibility. So basically, I take the average. So I can, yes, I can show you the equation later, the formula later. Okay, so notice that this 4069 is the upper bound, because when you are moving, so there are some cases that invalid move, so you cannot move in that direction anymore, right? So that means this is the upper bound. So in general, so this is my reward formula, right, as action J, right? So as basically the reward at this step, if I take the action, if I take the some action equals to the delta, the change on the board, plus this is a look ahead, right, from K to whatever in the future, right? So this is the look ahead part. But remember, we have to take in the random 2 pop up into account, right? So then this is sum over all possibility of random 2, right? So this is basically like the final reward formula, right? If I say, okay, so first of all, this P is basically the grid size, right? If the grid size is 4, then this one is 4, right? Then if the grid size, if it is 5 times 5 board, then this is 5. The P equals 5, right? Because you have to take in every possibility that the random 2 appears, every position of this random 2 appears.
But why is it only 4? If you have like 10 empty spots
after your, but the random 2 only appears on the rightmost, on the countermost, the most counter row or column, okay. Not any place, only on the edge, only on the edge.
And if you have a row which is full, then
yes, then it is invalid. Then you cannot, the random 2 won't pop up. Yeah, so this is a very subtle details that in the game that you can play later, right? So and then look ahead. So let's say remember our strategy was, our original question was, can I make 300 scores or 200 scores given 30 steps, right? Then to find the best strategy, as a 30 steps, so that we have to explore like I think I made a wrong thing here. So this should be 16 times 16 to the power of 30, right? So that is a huge amount of possibility in which I cannot really do that, right? And then in this case, if k equals 1, that means we don't do further look ahead. We just greedily make a move based on what we see on the board, right? Okay, so this is a visualization of how it works. There is let's say at this point we have a board at the J at this time. Then as I said, in order to make an optimal move, I have to try different move and then see what is the move that gives me the best reward, right? So that means I have to basically copy the board and then make a left, make right, make up, and make down, right? And I have to, in order to do further look ahead, then for each of them, I have to copy them again and then do the further things, right? Then you can quickly realize that, okay, so there's a lot of copy on the board. It's very inefficient. But we have serialization, we have protobuf, no, right? So we don't have, so we don't need to do this. We don't need to pickle it. We don't need to do any protobuf things. You can realize that, so actually, as I said, the board itself, it doesn't matter. So the structure, once you define it, it is fixed. The neighbor structure, the topology there is fixed. Whatever changes, whatever the state of the board is what matters, is what you really need to copy, right? It's basically the square, the value of each squares, the total score of the board and the current step of the board. And there is also like how many hammers left. And what is it? There is some random parameter. So those are the values that you need to copy, no other things, right? So you don't need to copy, you don't need to pickle and unpickle the board object, in this look ahead strategy. You only need to copy the dictionary here. Yeah. Okay, so that's basically summarize the look ahead strategy. And so now we can come to the very exciting part, which is the results and the findings. And the first thing is, again, so it's a whole waste of time. Like there's all the kind of like motivation behind this waste of time is doing this. Can we prove? Can we really make 30 steps, and reach 200 scores, right? And the answer is actually no, right? So this is a look ahead, different look ahead on 1, 2, 3, 4, and then you can see. And this is basically the lines, the curves with the opacity is basically we repeated the experiment for 10 times, and then the opacity curves are the every time on each round how it looks like, on the scores versus with respect to the steps, right? And the bold line is basically the average of all the trials, all the repetitions. And then you can see that even we increase the look ahead to 4, right? And then under 30 steps, you can at maximum reach 196, and there is only one. There is only one chance that you can reach here, right? So it's basically no, right? Like I've tried many times, it's not possible, right? So you cannot even get this level 2 weapon, in this under 30 steps. And then the level 3 weapon requires 40 steps to reach 400 scores. And then this is also not possible, right? So you can see like look ahead 1, 2, 3, and then you can see it brings you to 250, but nothing more. Like there is a couple of chances you can reach to 350 something, but that's it, right? So that's the best that you can get, right? So where the randomness come from? The randomness come from the random 2 dropping, right, on the counter direction, right? So this brings makes the game more probabilistic, right? Okay, then the level 4 and level 5 is of course impossible. Like 60 steps, like at most, the best that you can do is a 500, 500 score, right? So basically that means you cannot, this is not a 200, it's not 2048. You must use items there, right? But you know, some of you may look at this graph and look and think about it. You know, this doesn't show the advantage of using lookahead strategy. It seems that, you know, if I just greedily make a move, it seems fine, right? So especially when the number of steps is small, right? So I don't think there is much difference between different lookahead strategy, right? So, and then the question is, does lookahead strategy really works, right? Yes, so, but the only when the step is large. So when I put the x-axis to 1,000, right? So that means you take 1,000 steps, and then you can see a big difference between different strategies, right? Between greedy and look ahead. So for look ahead equals 3, you can basically double the score, right? Almost double the score compared to greedy make a move. Right? So this is but this advantage only appears when the steps is large, right? So let's say if you have limited time, like let's say you and your friend make a competition, and then you want to reach whoever has the highest score in 10 steps, then don't bother, right? Just you know, your IQ won't, you know, help you, right? So it's just you just play dumbly with your friends. That should do the work. Right? Okay. And then the next very interesting question is something like this. As you can see here, so you can see on some repetitions, in some repeats, in some runs, the curve goes flat. So that means there's no more score or whatever. So this basically means from this point, from 400 steps, you cannot really make any move at all. That's why the score is flat, right? And so that means the game is actually literally ended, right? So you don't have any choice. You don't have any action to take, right? And I wonder, what will the game end? When will the game end, right? So the question to ask is if I'm super good, can I play this game forever? Like, you know, if I have super good and I have time, can I play this game forever? So I increase the number of steps to 10,000. And this is actually what I get, right? So I found if I use greedy strategy, right? So you can see the right line actually end is around like 1,500 steps, right? And then it becomes, you know, kind of like a flattened. And then, but there is one case that you are able to play over 3,000 steps, right? And then for look ahead strategy, you in general get better, you know, better score, but also longer player time, longer playing time, right? So this is something that is very interesting. So that means that there is a limit. So you cannot really play forever, right? Okay, so then the third question is, how does the size of the board affect whatever the things that we discussed about, right? So the first thing is we can check 2 times 2 board, right? Which is a very small board that if you play 2048, can you reach that? Of course you can. You cannot, right? So I mean the best score that you can get is 68, right? And so probably you should call this game as a 16 because the maximum number that you can get is 16 here, right? So this is a different look ahead strategy on the 2x2 board, and this is how the score looks like. Right? If I increase the board size to 3x4 or 3x3, right? And then you can see that, okay, so in general you have longer playing time, right? So you can play long until you die. And then also the number of the scores that you can get is much higher. So previously you can only reach 68, and now you can reach like 2,000 something. Like of course it's the most optimal cases, right? But in general, like you can expect if you are very smart, you play the look ahead strategy with 3, then you can expect 1,200 something, right? at this level. And this is at 4, we already see that you can reach to 20,000, up to 20,000 scores, or even like 30,000 scores, based on the strategy that you choose. Right. And so this is a 5x5 board, and the competition is too big, and I don't have time to just plot everything. But as you can see, you can play up to 10,000 steps, and it's still not converged yet. And you know, and then you can get more than 100,000 scores, you know, on 5x5 or 5x5 board, right? Which is also very interesting to see, right? Okay, then the final thing is use items, right? So as I said, there are 4 items that we can use, but unfortunately, I don't have time to like wait. I don't have time to waste more, and so I just implement the hammer things. And then if you just look at the hammer, and it's already very complicated because look at the board at this point, right? So all this number can be knocked down, right? So that means the number of action significantly increase, right? And actually the increase is not constant. It's actually depending on how many values inside the board, on the board. So you can imagine if you have a very small, when you initialize the board, you don't have any value, or you only have one value on the board, then the number of action, the hammer action is only 1, right? But let's say when you play like a 99 step, 100 step, 200 step, you have a lot of numbers, values in the board, then the number of hammer actions, knockable values is also increased up to 16, right? And so to implement that, I have to add a hammer action to the sandbox, and I also have to improve the exploration of the reward function, right? So what does that mean, right? So for example, if I look at this board, of course I can knock down some values, but what if I knock down this 128? Is that a smart choice? Because it is possible that I try to knock down 32 and 128 in order to merge this 8 together. I mean, in a look forward strategy, this makes sense because you only tell me to look forward 3 steps. And then based on these 3 steps, I choose to knock down 128 because it's no use for me. But in the given steps of look forward, I don't see any chance to merge this 128. So therefore, I just knock it down, right? I just remove it because 128, the score has been calculated. In the short term, it has no use to me, right? It has no use to me in the short term. So I just choose to delete it. I choose to knock it down, right? So this is something that intuitively as a human, you won't do such thing, but your reward function doesn't care. They just knock 128 down. And then the other thing that we want to penalize is we just save it, save it to the end without using it. We save a lot of hammer, but we don't use it at all, right? This is also possible, right? So, you know, I just because this magical item is so precious, and you know, I don't want to use it, but in the end, the game is end. Then you never use it. Then this is also something that we want to penalize, right? So this is just one of the reward function that I designed, but unfortunately it doesn't work so well. So, but you can see already the difficulty, the challenge you have when you add more actions, right? So delta here is the same, and here you have the knock. So here we have 2 penalty term. We have 2 penalty term. The first penalty is about if you choose to knock it, right? If you choose to knock it, then you basically sacrifice, you know, the value that potentially can be merged in the future, right? So this value is served as a penalty here. So let's say you knock down a 2, then this V knock is 2, right? Because you sacrifice a 2, which can be merged in the future. Let's say if you knock down 128, then the value here is 128 because you sacrifice it for future merge, right? So therefore, this is the first penalty term. And then the second penalty term is about a function over steps, right? So let's say if you have a big steps, right? then you kind of penalize it because you're choosing not to use it. You're not choosing not to use a hammer. So basically, at the end of the game, you kind of have the desire of yeah, I have to quickly use the hammer because the game I start to lose, this kind of worry. So you want to simulate this tension into the reward function. And finally, the number of actions that you have, as you can see, is actually left, right, up, down, and then hammer over all the possible places, which is a lot, right? And so this is a hammer versus no hammer. Unfortunately, on the 16th step, it doesn't show up anything like useful, like interesting, right? And probably the reward function is not designed correctly, but you can later revisit the code and see, play with that. Okay, and that's pretty much the sharing here. And there are some random thoughts, and besides this look ahead philosophical things, like I don't want to talk about these things. Then the second thing is algorithmic, which is very interesting, is about the sandbox, of this game. And this AI strategy here, I believe there is a better way, like a reinforcement learning, which can chop down the exploration space or the solution space and makes the whole thing much faster and much smarter. And then you can look ahead even further, right? So this is something that's worth to explore. And then the game design and finally the product design is something that I want to highlight, right? I mean, if you think about this, like why do they design such game, right? So it's like a 2048, and but it's not totally like 2048, right? So I'm guessing there's this gaming company before Chinese New Year, they get together and they say that okay, so it's Chinese New Year, and everybody stacks together with their families and spending talking awkwardly with their parents and while playing their phones, this kind of things, right? And so we need to take this chance to increase the engagement of our players, right? So this is best time to make money, right? And but we only have 2 engineers and 1 month, right? And we cannot add a breaking change, and it's not worth it. It's just the Chinese holiday is just 1 week, right? So let's making money. Let's take this chance and making money in this 1 week, right? So I will give you 2 engineers, and then you design some changes to the game, and but not breaking changes because we cannot afford that. Right? Okay. How about introduce a 2048 like game, a mini game to the game, right? But then the question is, how does this 2048 innovative and addictive, right? So this is something like we always question ourselves, okay, so we have a new feature. How this feature is innovative, right? And 2048 is pretty lame, right? And most importantly, how does it even relate to the engagement, right? Okay, so then the decision is we design the level so that the player cannot win without magic items, right? And then the magic items can be only obtained by either in-app purchase or longer player time. Right? This basically close the loop of increasing engagement of our players, and then they can make money from that. Right? Now, of course, this is just my reverse engineering. If I'm the product manager, why do I come up with such lame game? I mean, this is the only reasonable logic behind that. Right? But I think there's also something that we can learn. I mean, of course, we are working in completely different domains. We are infrastructure software company, and most of customers are business customers. And they are gaming companies. They are consumer facing. They are building consumer facing applications. So psychology wise, they are very good at manipulating people and doing such things, right? But I think from the product design perspective, I think it's a very successful feature design, which basically solves the problem that low engagement in the Chinese New Year, and also without adding too much engineering effort, spending too much engineering effort in advance, right? Which I think is very very interesting. Right. Okay, so finally, that's pretty much it. And finally, you can look at the source code and play with that in this private repository. I don't write so many readmes here, but I think that should be enough. And the source code is very easily understandable. So you can play with that, use it as a sandbox to develop your own kind of more advanced AI strategy here. Also, the size of the grid can be changed, but don't spend your working time on this. Right. Okay. So that's it. That's the sharing here. Yeah. Any questions? Okay, so any question or comments here? If not, then let's go ahead.
What I found quite interesting here is your strategy of solving the problem and of somehow going to the problem. So I'm coming from a theoretical mathematical background. I would have just thought, okay, what are the properties of the game that I can utilize that I don't need to write the simulation? And you somehow write the simulation in order to look ahead and see what happens, which reminds me a little bit of somehow checkers or chess versus Go. When Go, you somehow need to build an intuition and play around a lot before you can't too much analyze the perhaps pure mathematical things. And I think you would have come to the same result by just somehow adding some numbers and understanding the theoretical concepts of the game. I found it quite this different somehow, because when you introduced, I thought like, why does he build the simulation in the first place? You can do it completely on mass. And this is two different approaches here. I found, just for me, an interesting insight. That you're thinking somehow is, okay, let's simulate it, and mine would be, oh no, let's completely calculate it through.
Yeah.
Yeah, I mainly have one observation. So I think maybe we should have chosen to pick the minimum reward, like other than the average reward. And I think since we are averaging or taking the minimum reward, the problem is no more probabilistic, I think. And this means like for each state of the board, there's only one reward. So maybe we can like use dynamic programming to make it more efficient and have better look ahead. Maybe I can calculate how much I can improve.
Yes, yeah, sure. I mean, so you are feel free to fork the repository and play with it. I think like right now we don't have any project involves reinforcement learning. I don't know whether we will have one day, but I think it's a very good practice exercise if you are into reinforcement learning and want to develop some try it on some games. I think this is a very good playground. Yeah. Okay. Yeah, so then that's it for today. Yeah. Okay, thank you.
Thanks. Bye.
Bye-bye. Thank you.